I want to talk just a little bit, take a step back and talk about bioinspiration versus biomimicry. A few years ago, this word biomimicry was used quite a bit, and I never liked it, and I still don't like it. And the reason is because there's a lot of things we can learn from nature, but just merely copying nature, I don't believe is the way to do it. I've given you a few pictures here. One of my hobbies is dogs, and this is one of my Irish setters. And if you look at the dog system, there's so many different breeds. They look totally different. There's Chihuahuas, there's Irish setters, there's Great Danes, and they're all developed for these different purposes. And in many cases, they were developed with a lot of human intervention. And you can see how great changes they can happen, and they all have the same DNA. So we can kind of affect these systems significantly, and I'd like to kind of keep that in mind as we talk about the integration between bio and nanotechnology using the gecko as a system. So I'm going to show you this movie. This movie is from Bob Full at UC Berkeley, and this is a movie with a bunch of geckos, and I'll start it in just a moment. And it shows, I just kind of want to use it as a motivation factor to show you how biology, how nature has evolved to do specific functions. And so in this case, this is talking about geckos and how they use their tails, and the rest of my talk will be on geckos and how they use their feet. But I think it's a really interesting example of nature in action.
Geckos are good climbers because of their sticky feet, but researchers are now finding out that their tails are just as important. A gecko uses its tail in two ways when it slips off a wall. If it loses one foot, its tail can be seen quickly touching the surface so that it can regain its footing. But if both feet come off, the gecko falls backwards and uses its tail like the kickstand of a bicycle to push itself back up on the wall. When placed in a wind tunnel, a gecko spreads out its limbs and uses its tail to help it glide. During freefall, it can snap its tail in one direction, which forces its body to flip in the other, so that it always lands on its feet. The researchers found that it only took about 1/10 of a second for a gecko to rotate its body. The agility of the gecko is inspiring the design of robots with mechanical tails that help them climb. The researchers think a gecko-like tail might be a useful feature for small, unmanned gliding vehicles. It might even help astronauts maneuver in space.
All right, so as that showed, the gecko's tail has a lot of different functions. And one important thing I want to point out is I'm an engineer. My background is in MEMS and nanosystems. And as engineers, we aren't biologists, and I don't think we should play biologists. But by working with biologists, we can really learn from nature and use the exciting things that biologists are continuing to learn, both from a macro scale, just by these things like analyzing videos of macroscopic animals, all the way to the micro scale of some of the things that Dr. Belcher talked about this morning, using bacteria and using molecular structure and learning from that and being able to utilize that. So that's kind of a highlight. So gecko feet. The fine hair adhesive has been found in lots of lizards and insects, not just geckos. Here's a bunch of them. And the interesting thing about this is there's a nanoscale structure to the foot. Here you can see this is a blow-up of one of the pads on the bottom of this beetle's foot. And you can see that it's extremely small. This is a 2-micron bar. But the thing that's the same about all these structures is that they all have these types of features on their feet. And here's some more. You can just see that they all have similar structure. They look a little bit different, but they all have these small nanostructured feet. And the gecko is exciting because it's kind of the biggest creature that uses this mechanism in nature to stick onto structures. And you can see in this figure here, this is a blow-up of the gecko foot. You can see there's a lot of structure here. And it's not just nanostructure. The animal is, of course, a relatively large animal. This one resides in our lab. His name is Dude, and he's about 8 or 9 inches long. So he's a relatively large animal. And the structure here is not only macroscopic, but he has kind of the milliscale with the feet and the toes, and then microscale. Each one of these bundles is about 10 microns. And nanoscale, each one of these little setae, which is what we call the branches on the feet, is even smaller. And then these branch out into little pieces on the very tips that you can't see, which are called spatula. And each one of those spatula is only a few hundred, basically about 150 nanometers in diameter. So there's the important point here is that this is a hierarchical structure. There's an incredible amount of geometry here and hierarchy. And so when we first started working on this problem, we wanted to attack it from that hierarchical perspective. We know how to couple, we know how to build micro and nano structures and have them work together, but it's, and so if we can couple them to the macro world and have them all work and communicate, we can build structures which behave in the way, hopefully in the way geckos do, in their unique ability to stick and unstick from surfaces. And so we, here's just a highlight, just showing again some of those different structures. And you can see these are nanostructured components down here, which sort of look similar to these. Again, they don't have to look the same to act the same. Like I said, you want to use the function and use the scientific principles, but that they don't have to look the same, especially when you're designing something for a specific function, which may be different than geckos. So here's just showing again that hierarchy. So the main forces involved in gecko adhesion is a van der Waals force, which is a very short-range contact force that occurs when two surfaces come within very close contact. The van der Waals force by itself is very small, but the unique thing about the gecko is when you have millions of these little hairs and they all get very close together, the force adds up to something very significant. And about, I don't know, almost 10 years ago now, there was quite a big argument in the scientific community about what caused geckos to stick to walls. People thought it was capillary forces, people thought it was van der Waals forces, suction. There were all sorts of theories about it. And some researchers from, a collaboration of researchers from Berkeley and Stanford and UCSB, as well as other people, did some unique experiments using MEMS force sensors and relatively definitively proved that van der Waals forces was a dominating force involved. So this tiny force that occurs when atoms get close together can add up to something large enough to hold a gecko on a wall. And I'll show you at the end of the talk, we can use this to actually hang a lot of bigger things than geckos off walls as well. So what we wanted to do was create controllable conformance, and this is from a paper from a team in Europe that was working on this a few years ago. They built a material that was just nanostructured, and they put it on a soft backing and stuck it to the wall, and stuck it to this toy Spider-Man, and stuck the Spider-Man to the wall, and they had to push extremely hard to get him to stick to the wall, but he did stick for a while to the ceiling, and then he fell off, and he could never stick again because the nanostructure was damaged due to how hard you had to push to get surface contact. And so our approach was quite different. We wanted to create a controllable conformance and use hierarchy, much like the gecko does, in order to get better surface contact. Because, as I said with the van der Waals force, by each individual hair creates a very small force, but when you add them all up, it becomes a significant force. But for that to be successful, you have to have extremely good surface contact. So if it's a rough surface, and you push a flat thing against it, you don't get much surface contact at all. But if it's a rough surface and you can mold your surface to it without damaging it, then you get a lot more force. So that's what we were trying to do using microtechnology, create controllable conformance. And so a few years ago, I had a very creative student who built these structures. And like you see here, they don't look like the gecko feet, but they function in much the same way. We made them using microtechnology, so you can, they were made in a batch process using a combination of plasma etching and deposition, standard kind of MEMS processing, and so you could make a whole lot of them. And we also integrated, so those were micro-scale structures. Each one of those little squares was about 150 microns. So you can see those were micron-scale structures. Then we integrated those with nanostructures. We built polymer nanostructures out of a photoresist-based polymer, again using a kind of etch and deposition technique. And you can see that these, he called them organorods because he used the combination of organic-looking nanorods. They weren't organic. But anyway, they have properties that are approximately that of the gecko. In terms of stiffness. So you can, here's the highlight of the mechanical properties. The geckos, the Young's modulus of beta keratin, which makes gecko, which the gecko setae are made out of, are very, depending on the measurement, people have reported a lot of different numbers. So that's why I have Young's modulus from 1 to 15 gigapascals. But again, they were relatively similar in property. In addition, gecko hairs are highly hydrophobic. They're hydrophobic, we speculate, for a number of reasons. Biologists think that the hairs are hydrophobic in order to to help the geckos keep them clean and to keep them from sticking to each other. If the two hairs stick to each other, then they don't really function as, then they function essentially as one hair, and it's a bigger hair and you get less surface contact. So we also made our hairs hydrophobic so that they would also be able to be used over and over again. So we tested these, and sure enough, with the hierarchical structure, the adhesion was much greater than using either flat structures or just nanostructures on a flat substrate. And they also lasted better. If we tested nanostructures on a flat substrate, this is, oops, the image isn't quite showing up. This is number of repeats versus adhesion. And so you can see that the flat substrate, the adhesion decreases quickly because they're getting damaged as you smash them into the surface. And so we were pretty excited about this. Our adhesion values were still not that of the gecko, but it showed some significant promise. But the other interesting thing about the gecko and what makes it exciting is not just that it can stick. I mean, we can build adhesives. We can build tapes and glues and things that stick really well. But the adhesion, the gecko can do this quickly, and he can stick and unstick. It's not just that you see one stuck to a wall that can't come off. I mean, they can run around extremely quickly. And so we wanted to be able to copy that as well. So we used instead of building them out of silicon or silicon dioxide or polymer, we built them out of a magnetic material, which would allow you to excite them and move the microstructure, which would in fact peel the nanostructure off of the surface. So we just use the concept of if you put a ferromagnet or ferromagnetic material in a magnetic field, it will try to align. And so we could build actuators that way. And so this is what that cycle of actuators looked like. These are nickel and later nickel iron structures. They still have polymer nanostructures on them. And what happens is when you apply the magnetic field, they were set on top of a magnet. And when you turn the magnet on, we used an electromagnet that you could turn on. When you turn the magnet on, they all rotated sideways. And you can see in the next here, again, we made large arrays of them. And so this is when the magnetic field is off. And then when you turn the field on, they all flip over and kind of peel away. And so we tested this using a adhesion tester with our collaborator, Edward Arts, who was at the time at the Max Planck Institute. And we tested these structures there, and we found that indeed they did behave as expected. And here's the experimental result. This is pull-off force versus preload. This preload is how hard you have to push on it how hard you push on it before you pull it away. And you can see that when the magnetic field is absent, there's significant adhesion, and then when the magnetic field is on and they're all twisted over, you don't get much adhesion. But more exciting is the actual peel-off result, which is shown here. So this result, hopefully you can see this, I apologize for the small size, but this is the preload. And then we unload it. This is all with the magnet off, so the structures are in full adhesion mode. And then we hold it there, and then we turn on the magnet. And as you can see, it snaps off immediately. So we were pretty excited about this, being able to reverse the adhesion properties. And this is another movie. My student who did a lot of this initial work actually went on to do a kind of unique thing after he graduated. He got a call from the Discovery Channel, and they were filming this. They were planning this new TV show, and they invited him to be the host. And so he's the host of this show. You may have seen it if you're into science shows in the Discovery Channel. It's called Prototype This. And it just started airing in October. And so they filmed a gecko episode, and I found the video on YouTube, this little clip of the gecko episode. They built gecko, basically Spider-Man gloves, you know, the classic, everyone asks if you can build Spider-Man gloves. They built Spider-Man gloves, and a few weeks ago they climbed they had a climber wear the Spider-Man gecko gloves and climb the UC administration building. So I have a little in Oakland, and I have the clip of it, so hopefully this will play, and we can see it. It was on the news.
There was a pretty amazing sight in Oakland today as a UC researcher climbed up a building using technology discovered by studying the gecko. It's part of a show being taped for an upcoming science show. Wayne Friedman has our story.
It was one of the least likely places to emulate nature.
Geckos climb.
Dr. Mike North, a materials expert at UC Santa Barbara and one of the hosts for a television show called Prototype This. Today, they attempted to climb a cinder block wall using this device that, in theory, uses thousands of little fish hooks as grippers.
You get enough hooks to grab on, then you can actually get it to stick pretty good.
They emulate gecko feet. Alan Asbeck developed the first version of this thing at Stanford 4 years ago.
This is the first time someone's actually climbed with it.
What odds do you give it?
80%.
80%.
80%.
Are you doing the climbing?
No.
That task went to 136-pound Lynn Verinsky, a professional climber who appeared to be brimming with confidence.
Honestly, it's going to be perfectly safe. It'll be perfectly safe.
How do you know?
Because of liability insurance.
With a mattress below and attached to a safety rope, Lynn began her 60-foot ascent. It did not come easy. But unlike geckos, humans adapt in minutes, not millions of years. And while she wouldn't want to do this without the safety equipment, Lynn made it to the top in a perfect pairing of Hollywood and science. So you're the first human being to officially emulate a gecko.
Wow. And what a privilege that has been.
From Oakland, Wayne Friedman, ABC 7 News.
Wow, next stop, Half Dome.
That was so cool.
All right. So just to show you a couple more things that we're working on in the future, it turns out, in a collaboration that I have with Jacob Israelishvili at UCSB, a material scientist, he's a tribologist. He's been working on the role of friction that is in gecko motion. And friction turns out to be extremely important. And so we have a collaboration with a company, IMT and ARL, to build friction actuators into our gecko adhesives to greatly enhance the adhesion. And so I'll just show you what those look like. So in those devices, we actually want to apply friction. So we want to apply lateral force to increase the adhesion properties of the gecko. For example, when geckos stick to walls, they use a lot of friction because the force as they put the claws out, there's a lot of friction involved as well. And so we have these devices here which are latching actuators, which actually, so here's the gecko pads, and then these actuators are thermally heated, so it opens up and then a latch comes down to hold the devices in a steady friction state with no power. So we're really excited about that, and we're hoping that that'll enhance the adhesion. And it's also, again, electronic. We can turn it on and off. And so we can allow the device to stick or not stick as necessary. So with that, I will summarize. The takeaway points are, I think this gecko story is exciting because, I mean, people like geckos. I'm not sure why, because they're really mean. The one we have is really mean, but they look cute maybe, and they're the motto for Geico. But it's an interesting system because it's a hierarchical system. It uses meso, micro, nanotechnology all working together to make it function. There are a lot of things we can learn about it. There's this interesting and fun synergy between biologists and engineers. I think it's a great time to be an engineer. Biology has come so far, even since I learned biology starting to learn biology in high school. It's so much more exciting now because the chemistry is so much more well understood, and the materials experts have made such large leaps. And so I would challenge people who want to work in this area to learn the language of biologists. As engineers, I don't think we should become biologists, but I think we need to learn the language. And the gecko story has just been a really fun introduction for me into the kind of realm between nano and bio. So that's all I have. Thank you very much.